So we're very happy to have today Audrey Huang. Audrey is a PhD student in the UIUC down the road and is doing really exciting work on an intersection of reinforcement learning and reasoning with large language models, which is probably maybe the most exciting place to be right now in shaping the future, and is going to tell us about some of her work. Audrey is going to be here throughout the day, and you can also catch her at tea time at 3 p.m. Okay. Thanks,
yeah, thanks for having me to present my research. For some background on myself, I worked on reinforcement learning theory for. Should I put it closer?
Yeah, we can probably, or maybe it's not on.
I'm hearing you fine.
We can hear you.
I'll just put it here. Does it work? So, I worked on RL theory for most of my PhD, and then in the past 1.5 years, I've been thinking a lot about how to make RL work in language models. If we look at the past year, I think it's still surprising to see how fast language models have become like basically a ubiquitous part of our lives. So starting in like January 2025, just 1 year ago, DeepSeek was released, and then we have the rise of reasoning models where like in the span of a year, they quickly solved many of our competition math benchmarks, won gold in International Math Olympiad, and now they're used every day in academic research, in production level coding, and all these events have happened so fast that it's sort of hard for me, at least, to remember what it was like before we had these models in our everyday work. So yeah, I think the reason why I'm interested in language models is because this is a place where reinforcement learning has seen incredible success, maybe for the first time in kind of incentivizing general advanced behavior. And it's the driving force here behind the reasoning behavior that we see in frontier models. So, before DeepSeek, we had GPT-4o, and the training paradigm here was mostly pre-training. So you have large scale next token prediction, which is like supervised learning on natural language demonstrations where you have like a lot of text from the internet, and the model is trained to predict the next word from the given context. Obviously, there's a lot of randomness in language, so the model that you get out of next token prediction might not give you the behavior that you want. And so the role of reinforcement learning here is mainly to improve the model's behavior through trial and error with a reward signal, and to try to align the model with human preferences. So it's mainly for conversational alignment rather than reasoning. So it makes sense that with this kind of training that maybe advanced reasoning behavior isn't going to emerge. And if we measure the performance on AMY, which is a competition math benchmark, let's say correctness out of 15, there's a huge jump between GPT and DeepSeek. And the reason why this happens is because of RL post-training. So RL post-training here is mainly to induce chain of thought reasoning, which means that instead of directly outputting the next, like directly the answer to a given question, you incentivize the model to produce longer responses, and this helps the model to be able to represent more complex functions. And so the role of RL here is to, by just RL on response correctness, it's able to sort of induce the behavior that we associate with reasoning, like thinking for longer, backtracking, self-verification, etc. And now with GPT-5, we have expert level performance on a level that even previous models didn't have. And these are extremely long horizon reasoning problems that require many steps of thinking. And so now we're in this domain of agentic RL, which is closer to what reinforcement learning started off as. You have a model, and it's reasoning, but also making tool calls to external APIs like Python to verify its responses and reduce compounding error and to be able to handle longer context and perform even deeper reasoning. So I think that this is really the time to be thinking about RL in language models. And so the overall question that I am interested in is how we can train agents that autonomously advance their capabilities. And I think that the success of RL in language models is very surprising from, I guess, if you look back to before language models. So reasoning requires thinking and planning over long horizons. And the way that it's being trained in state-of-the-art reasoning models like DeepSeek is actually very simple. So you just have a sparse sort of response level reward telling you whether the entire thing is correct or incorrect. And so there's lots of results from RL theory telling us that when you do this kind of thing over long horizons, that there's compounding error, there's the critical horizon, and this should be computationally or statistically infeasible. And for this reason, I think RL has seen limited real world deployment before language models, where in order to get something like the Rubik's Cube on the left, you basically had to do like that in the middle. And so I think it's interesting to think about why RL is so successful in language models like never before. And what I want to talk about in this presentation is sort of a series of works that show that what's different about RL in language models is that the post-training process doesn't start from scratch, but it starts from a highly capable pre-trained base model that has a lot of natural language understanding and powerful representational capabilities. So to show maybe a hint of why this is the case, we saw previously that RL post-training and reasoning models is inducing chain of thought thinking, but in 2023 we already saw that large language models are capable of eliciting this behavior if you just prompt them with things step by step. And similarly for agentic RL, existing models are able to sort of elicit action sequences and roll out commands like verify or wait or update from the training that they had previously. And so this sort of iterative series of gaining capabilities and advancing them with RL and repeating is one mechanism by which agents are able to advance their capabilities. And maybe what I'm interested in here is how can we make this happen more continuously for even harder problems. Okay, so the first step for doing that is
I have a question. So this post-training paradigm changed a lot from May 2024 to now. So why do we think that this agentic RL is kind of the way to go? I guess you said that
I don't know if it's
you wanted to focus on.
I don't know if it's exactly the way to go, but it is the current focus of large scale models. And maybe one difference is RL post training with chain of thought reasoning is sort of trying to do single shot reasoning. So you have a problem and you want to do everything in a single trace for a very long time. And for extremely difficult problems, this reasoning trace becomes very long and the search tree becomes very deep. And so being able to kind of control your thinking effort, control the context length, use external tool calls to mitigate error compounding is one mechanism by which you can sort of enable deeper searching and kind of iterative planning and refinement. And I think it makes sense in general that this reasoning and planning is sort of coming back to this iterative decision-making setting rather than just being a contextual bandit. Okay, so so the question that I'm going to discuss here is how RL post-training can best leverage the powerful base models that come out of pre-training or previous training. And a high-level overview of the result is that what we get is a mathematical framework for how RL interacts with the base model, for how it amplifies the latent capabilities in this pre-trained base model. And this will generally enable new algorithms in the sense that we can sort of increase the ceiling of performance by optimizing the potential in the base model for downstream improvement in post-training. And also we can design post-training algorithms that, given a base model, maximize the performance that we extract out of it. Okay, so before getting into the details of the talk, I want to give some high-level overview of what RL post-training algorithms look like. So in RL, there's basically two main steps. The first one is that you want to specify a reward that I'll call R that captures the true task behavior. And this is believed to be specified by some like true underlying reward model R star, but this is extremely complex, and so we generally don't exactly have R star. And I'm going to be operating this contextual bandit style setup, which is reflective of how people think about maybe chain of thought reasoning in language models, where you have a prompt X and a response Y, and you pass this through the reward signal R, which can be a pre-trained model or something computed, and this gives you the reward RXY. And so in RL, what you do is you maximize the reward of a policy starting from the base model. And so here the learner starts from the base LLM in blue, and I'll call the base model PyRef. And I'll model this base language model as a conditional probability distribution. So you have the prompt X and you have responses Y, and then Y is drawn from like pi given X. And the goal of RL is to just maximize the expected reward on this reward signal to induce the desired behavior. There's two main types of RL post-training algorithms. The first one, the first group I would say are policy optimization methods. So these are methods that essentially use backprop on the reward objective to produce a better model. And this includes algorithms like PPO, GRPO, and expert iteration, where you collect a bunch of responses, filter them for correctness, and then update the model again. And the other broad group of methods are test time methods. And these are algorithms that don't take any gradients, but they modify the distribution of the base model purely at inference to produce a better response y plus. And maybe the most well-known and widely used example is best event. So best event is a very simple heuristic for doing test time search over the responses of the base model. So all you do is you sample n times for a given prompt, evaluate the rewards of those responses using your reward signal, and then you just pick the response y plus that has the highest reward. And so this is taking the argmax over y1 through yn. And empirically, this is an extremely effective and very simple procedure. So what I'm showing here is the performance of best event on the math benchmark for various base models shown in the different colors. And on the y-axis, I have the percentage correct as the number of samples in best event scaled on the x-axis to the right. And so you see that regardless of starting point, most of these models are hitting, like essentially 90% accuracy as you scale n. And this is a computational regime that's emerged in LLMs called test time scaling, where you increase the amount of computation, or n here at test time, and this enables you to approximately maximize the reward of the output response.
Question?
Yeah.
So in a really long horizon problem, like if you're going to have to do a lot of thinking,
Yeah.
How do you, without doing all of that thinking, how do you pick the best choice at an intermediate point?
Oh, do you mean like perhaps you don't want to generate everything? Like you don't want to generate all responses to the end and then
Well, you don't want to complete your thought chain because that's very
yeah.
long.
Yeah, I think that there are methods to do this. Maybe one representative one is like when people use process reward models. So these are similar to value functions in RL, but they can take just some like prompt and partial completion and tell you how likely it is to end up in a correct answer.
Is that value function, I mean, in typical RL, that value function is trained, right? This is a test time
Yeah, so
method, but the value function would be trained.
it's an auxiliary, like pre-trained value function, and this has been used, but not to, I think, empirical success. Yeah, maybe that's. I don't think that there is necessarily a extremely good method out there for doing this, but maybe others know better. So yeah,
So did you say it has seen success or it hasn't seen success?
no,
It
I
hasn't.
think yeah. So like value functions have been used a lot in RL and robotics, but I think there have been many attempts to use value functions in LLMs, and maybe surprisingly so far they haven't been used in deployment that I know of. But I guess like I think what I've heard is that maybe they will, like they're useful for long horizon credit assignment, and maybe the issue with like existing value functions is that they're very noisy. So perhaps if like the quality of value functions are improved, then maybe they can be very useful.
Do you think there's any fundamental barrier to like how well we can estimate these value functions?
Yeah,
Because of the long horizon nature of like task learning.
I do think so because maybe I think the current barrier is maybe related to. I mean, I can't exactly say because I haven't really like utilized them that much, but you know, when we think of responses as like a sequence of tokens, you want your value function to be accurate on like many of these tokens. Otherwise, you need to decide like which tokens to query on like many different distributions. And so you sort of need to learn a value function that's good in like a very like large area of the response space. And it seems to be difficult right now, which is maybe a little bit surprising given that, you know, we can learn a generator that's pretty good on like a large part of the response space. So right, so with best event we're in this test time scaling regime, and yeah, it's widely used in O1 and other types of frontier models. So in this talk I'm going to focus on best event, which is a test time method, and it's gradient free, as a representative sort of framework for general RL post training. This is not perfectly true, and that's something I'll return to in future work. But I think it's a useful place to start because there's this growing view in the community that RL is just amplifying latent capabilities in the base model, and that stems from papers like this one that show that test time methods are competitive with policy optimization. So on the x-axis there are different reasoning benchmarks. On the y-axis the percentage of correct, and then it's comparing the performance of GRPO versus a gradient-free test time algorithm, which are similar in many cases. And also this pretty famous paper by now. Yes.
So I'm a bit confused with this comparison because presumably, especially the purple bars are very affected by just how much test time. The purple bars especially are affected by how much test time. Right?
Yeah.
So as you said before, if they put tons of test time, eventually, fine. So, how should we read this? Like, how much test time is like policy optimization worth, or what's the?
I think that's a good question. At least, like the main. I think in their paper they did something reasonable, and I don't know the details. I think the main gist of this is that you can say like by showing that the base model, like with prompting, you can elicit certain behavior with the base model, or with sampling methods, you can elicit certain behavior from the base model. Sort of shows that this like the base model has a latent capability, but it just needs to be like extracted somehow.
This particular test time method does not use any rewards.
So
It's not best event. This is something else.
yeah, but what?
This is doing MCMC on. This is the MCMC paper, right?
Yeah, but I mean, I know it's not best event. It's just like showing that you don't have to use gradients to get good.
Okay, I'm still a bit Yes, this is what I'm supposed to get from. Okay, it's.
I think okay. I guess this is how I think of it. I feel like, you would think that policy gradient can do a lot better than test time methods if you're just like searching over a response space, right? Like policy gradient, you can work with the parameters, you can do something more than if you just have to like generate a lot of sequences and deal with the stochasticity of sequences. And so somehow, like, even if you do that, you're able to get performance that's like competitive with what you get with RL.
Okay, it's continuing.
Okay, yeah.
Question about the benchmark itself.
Yeah.
So technically speaking, if you have like single choice problem, like best of 4 can be like a perfect accuracy, right?
So if you have a one.
Like single choice problem, it just gets A, B, C, D for every problem. Like for fair comparison, you have to like unless this is like a form of theorem proving, it's not a fair comparison. Like you have to choose the final answer, single answer. It's not like a best of n.
Sorry, what's the? I don't think I
mean,
fully understand.
The comparison is not fair because the custom scaling method here can have multiple opportunities to guess the answer.
But I think the answer can be like maybe that's not. I mean, you can say the same for let's say like. It's just like for something like math, there's many possible answers. So
Even these data sets is fine. These data sets have the range of answers is very large.
like the answer is not multiple choice necessarily, but it's like
Yeah, but I guess we need some information like about the range of the answers to understand the non-triviality of this experiment.
yeah, I think like I fully understand that. This is just a little bit vibey, so
Sorry, so are we using a trained reward model to judge the best of the n
this
generation?
one uses log probabilities of the base model, so it's using even less information than if you use.
So just the most confident.
Yeah, essentially. Right, and then there are other results showing that if you compare the test time scaling of a base model in green versus the post-trained model in orange, that the peak performance of the base model is higher than the peak performance of the post-trained model. And so in this sense, best of n maybe is optimization free, and it's just like a simple test bed where we can isolate the role of the base model and ask some maybe computational statistical questions about how many samples do we need to output a good response, and what are the properties of the base model that matter for having good performance. Okay, so this is an outline of what I'll talk about. The main question is just about how RL post-training interacts with the base model and what properties. So in the first part, I'm going to look at test time scaling with best of n, and what we show is that there's a property of the base model called coverage that governs post-training improvement, and this is a quantity that we can optimize in pre-training to improve downstream performance. And this part is just using true rewards, so we're in this like verifiable setting. The second part sort of completes the story by adding in learned reward models, which are noisy and have error from data. And what we show is that, okay, maybe the first part establishes the ceiling of performance or ceiling of performance lift available in post-training from a pre-trained base model. And you lose some of that performance with a learned reward. And standard RL algorithms will overfit to these reward model errors, but we can come up with an even better algorithm that will avoid this problem. And yeah, some future work. Are there any questions before I keep going? Okay, so the first part is on analyzing how test time scaling with best of n works. And what we want to understand is what properties of the base model matter in best of n, and how we can optimize these properties in pre-training, which will result in better post-training quality. And so if we go back to this previous figure showing how test time performance in best of n scales in the math benchmark, we're going to operate under the assumption that we have the true word r equals r star, and we want to understand what shapes this test time scaling curve, which is how performance grows with the compute n. And this will allow us to formalize this concept of like what capabilities the base model has and how RL amplifies them in post-training. So the y-axis here is r star, and having the setting where we have the true word in r star captures a dominant post-training paradigm in reasoning models called RL with verifiable rewards. And here r star is just some computable objective function of the response. So there's no noise or estimation error in the value. And typically it tells you whether the final answer in response is correct, whether a proof compiles in lean or whether code pass unit tests. And to formalize the problem a bit more, we're going to measure the performance of best of n relative to a target policy pi star. So this is a distribution over responses, and it represents this task-specific behavior with high reward. And pi bon in orange is going to denote the response distribution under best of n on the base model pi ref in the gray line. And we want to analyze the performance gap under r star between the performance of pi star in blue and the best of n distribution in orange, and how this gap sort of shrinks as we scale test time compute. So in what way can best of n actually amplify capabilities in the base model? So what I'm showing here is some illustration of the base model's distribution in gray and the sort of target distribution pi star in blue with responses on the x-axis. And intuitively what best of n does is that it amplifies the probability of seeing any given response by a factor. And so this lets you sort of like pull good responses from the tail of the base model. But for a given n, you essentially cannot really simulate responses from pi star where the distribution of pi star is much greater than, the probability of pi star is much greater than this model, which is shown in orange. And so intuitively the gap is going to be the mass under pi star of these responses. And we formalize that in this guarantee. So you show that for any target policy pi star, any target behavior, and a given best of n budget n, that the suboptimality between the performance of, like your target performance and your best of n distribution is upper bounded by this quantity in green, which is sort of an upper bound on what I just mentioned, but it's the probability under pi star of responses where the ratio of pi star over pi ref is much larger than n. So these are just intuitively responses that are hard to simulate. Yeah.
Very good.
No. Just to, maybe you said and I missed it, but is the sampling temperature considered to be part of definition of pi star?
So pi star is just a distribution of responses which can be induced by like temperature sampling on a softmax distribution, but it really is just a generic, kind of abstract target behavior.
But changing the sampling temperature will change the typical set or the probability for a particular. Okay, so this, if I have two different softmax temperatures, this will mean in this settings two different pi stars. Is that correct?
Yeah, but
Pi ref. I'm sorry. Yes.
I think I mean, yeah, like both of these like distributions, pi star and pi ref, are sort of just distributions of responses. So if you change the temperature, the bound still applies.
So maybe I misheard, but the way you described is that what best of n is doing is it's not shifting the mode of pi ref.
Yeah.
But you have reward verification, right? So wouldn't that shift? Why is the mode not shifting?
It is.
So basically, anything with high likelihood under pi ref is going to stay high likelihood under best of n.
It's like when you have the reward, like it can have high probability, but if it has 0 reward, it's not going to be selected by best of n. So it's like you sort of magnify the probability of seeing rare responses,
Yep.
and then you choose like the best one. So you can upweight like high reward responses, which as a result downweights like low reward responses. So like it is shifting,
Okay.
It is, yeah.
So this it's kind of like asking how can you use rejection sampling
Yeah,
from
yeah.
one distribution to simulate another?
Yeah. This is essentially like a approximate rejection sampling problem, and like many of the proof techniques come from approximate rejection sampling. So the gap between the best of n distribution and target policy is upper bounded by this quantity that we call the coverage at n. And it's denoted cov n pi star pi ref, and it's represented by this green area. And intuitively, it represents the difficulty of eliciting the target behavior from the base model in n attempts. And you can view it as this expressive CDF of the density ratio. And using standard like Markov inequality, you can transform this coverage at n into more familiar divergences, like the KL divergence, where the coverage is upper bounded by KL over log n, where n is your sampling budget. And this maybe is better for seeing that in the bound, the gap will be smaller when the base model is better aligned with pi star distributionally, and also asymptotically as compute scales, this gap goes to 0. So what we say is that given a base model pi ref and a target, the test time performance is governed by this CDF-like function or the coverage profile, and this essentially governs like the shape of the test time scaling curve for a given base model. And the coverage is a property of the base model itself and maybe some abstract target behavior you want to elicit.
So, I mean, you said this controls it. This is just an upper bound, though, right? I mean, it's
Yeah.
so it's
We have a matching ish lower bound. This is essentially like writing it as let me just represent it pictorially. Writing it as like this. So I mean, the tightest bound you can get is this like orange thing. You can show that this is tight because this is the like sort of a information theoretic approximate rejection sampling lower bound, where like if you have only n samples and you're rejection sampling from the base model, you're just not going to see like those responses from pi star very often. Writing it like this is sort of for convenience when we use it later because like for like pre-training purposes. Like you can write this as an expression, but it's a little bit complicated, and this will be easier downstream. Does that answer your question?
maybe.
Is there?
I mean, I'm still a bit like you. Are you saying that? So this is tight or not? So is this? I guess you said is this kind of tight or not? I don't.
I mean,
this expression.
does it like? I mean, sort of. I don't know.
Okay, we can.
Like, I think there are some conditions. I mean, there are like additional factors, but they aren't really like the dominant factors that.
I guess the question is, can the gap? Are there distributions in which the gap would be much lower than this
Yeah.
discover.
Sure, yeah, because I mean, like one source of looseness is that you're converting from like a reward maximization problem to like a distribution matching problem. And so you can imagine if you have,
Oh, okay,
like binary rewards,
right.
that's much easier than,
Um,
this is like sort of. Okay, beyond maybe being descriptive in theory of this performance, why does having the coverage profile give us utility? So what I'll show in the next part is that it can provide guidance for developing the base model, and we can use it to derive new algorithms for optimizing coverage. To give a sense of why coverage is useful for improving the base model, I'm going to show some results in like a small scale testbed in graph search. And basically what we do here is we pre-train on a diverse data set where the prompt is some deep and densely connected graph, and the role of what PyStar does is it finds a path from start to goal. And so the base model is just trying to copy this distribution. And this is sort of like a kind of a mock-up of maybe stepwise decision making and reasoning problem. And so how to read this graph is that it's showing that in this test bed over the course of training, that the coverage of the model is correlated with test time performance. And how to read it is that on the y-axis is the performance of best of n with n equals to 8, and on the x-axis is our metric called coverage. And so each of these dots is like one of many training checkpoints over many seeds. And over these checkpoints, essentially coverage is predictive of testing performance. And this is something that also holds as you scale n. So here's n equals to 16. And this gives us some hints that if we can pick the checkpoint with a better coverage, then we can translate that to better test time performance with this event. So the first part, we quantified the capabilities of the base model with a coverage profile, and this forms a ceiling for test time improvement. And we're going to look at.
How do you estimate the coverage?
I mean, I think that it's not something that you can necessarily estimate in general, because you need the probabilities of PyStar. So if your data is from demonstrations, like human demonstrations, then you don't necessarily have access to this PyStar. But there are sort of versions of it that you can estimate and use for like optimizing coverage.
So in the plot that I saw,
Yeah.
so you were
Oh, in
plotting
this
coverage
plot.
on the x-axis.
Yeah, for this one, it's just descriptive, so we know what PyStar is. It can we can exactly specify it in these graphs because we generated data from it.
Oh, you generated.
Yeah, we generated the data. So here it's not so much like showing that an algorithm works, but just that this metric, if you can estimate it, is correlated with.
So this is self-generated data. This data is like you have PyStar.
We have
It's
yeah,
synthetic data.
exactly yeah. So here we go.
It's just different checkpoints along the way of training.
Yeah, it's just different checkpoints too. Okay, so we just saw that in post-training, the base model's coverage over good responses matters. But what happens in pre-training is that the base model learns to imitate the target behavior PyStar from demonstrations. So typically what happens is that the base model PyRef is trained to minimize the KL divergence between PyStar and itself. And this is the expectation over PyStar of log PyStar over Pi. And there's like a small like sort of gap that I'm skipping over here, which is that typically pre-training data is like different from post-training target behavior, but I'm just going to treat them like they're the same here, and if they're different, then there's going to be some additional distribution. So looking at these two objectives shows that there's a mismatch between what we care about in post-training and the kind of behavior or properties that we get out of pre-training, which is that in post-training what we want is coverage, and this is sort of a distributional metric that's sensitive to tail behavior. So essentially, as we go deeper into the tails of the base model by scaling n, we still want the distribution to represent good responses. But pre-training is trying to optimize the mean of log pi star over pi ref. And as a result, it's possible to lose performance or lose representation of low probability events. And so what we're going to analyze is when coverage develops in pre-training, even though you're using a different objective. So at least theoretically, if your target behavior is well specified, so you have a policy class pi, so it could be a transformer, that can represent pi star, and you have m training samples, then we show that pre-training is able to implicitly optimize coverage in the sense that the coverage is upper bounded by the complexity of the policy class divided by the number of samples and log n, which is the test time budget for any n. But this may not be the case under misspecification, which tends to be the case in practice with pre-training. And then we have to ask if coverage improves in general. Going back to this graph data set, what we see in pre-training is that the KL divergence, which is plotted here, decreases monotonically over the course of training. And previously we saw that coverage is correlated with best of n performance, with coverage on the x-axis and performance on the y-axis. If we overlay a graph where we have KL on the x-axis and performance on the y-axis, we see that KL divergence, where each dot is a different checkpoint, we see that KL divergence is not predictive of tested performance. And if we look at the sort of progression of coverage overlaid with the KL divergence in black over the course of training, KL divergence monotonically decreases, but the coverage profile for different ends, like 2, 3, 4, provides a more expressive sort of picture of training, in the sense that there's some middle point where like the coverage is extremely good and then increases, and as KL divergence decreases, it decreases at the cost of coverage of the target behavior. And the reason why this happens is because this okay, I didn't go into detail about the test bed, but it has a lot of different behaviors in it, and so learning all of these behaviors is difficult for the given number of samples for the model size. And so at the middle point where the coverage is really small, the model is sort of good on, or pretty good on, all of these different types of behaviors. But in order to decrease the KL divergence further, the model is sort of sacrificing behavior on the tails in order to sort of snap to the more frequent types of behaviors. So this is a case where there is no specification, and we see that coverage is not decreasing monotonically, at least in training.
So I have two questions here. So, we're showing in the small plot, we're not seeing, if I understand correctly, the final performance, when you're just showing your midpoint.
No, we're not seeing.
But here the R star that you in the plots that you kind of half erased.
Yeah, that's best of n performance.
So that's best of n performance.
Yeah. So if you do like n equals to 1, then you know the performance KL will be aligned with.
And what's those numbers? Is this logarithmic, or will you say 4.6, 5.7?
That's
curious,
a good question.
Like I'm curious, like what scale of numbers are we talking about here? When
I mean, I think this is not a super long horizon problem. So this is really just like.
So we're really talking about
What do they
best of 5? So this is really like best of 5 or something like that, or I mean, I'm not sure exactly what.
This is just n, I guess.
This is
I mean,
n.
it's
So
just
it's just
n
n.
with
So
some
it's really there's best of 5, best
Yeah.
of 6. So it's really.
It's not like a very wide range.
So that means that even in the beginning, best of 6 basically solves the.
Wait, isn't it n over 2? Because there one.
Oh, if you have to over 2, so best of 12. Like initially, you already. If I'm just going to say, so read this correctly. Then even initially, basically with a very few number federation, right? Best of 12 or best of 6 or something like that. I don't know. Or best of some single digit number would be completely perfect here. Is that?
Yeah, I mean, basically there's 3 tasks, and so the model will randomize over them after pre-training, and that's why like a small constant number of responses works. I mean, this is a very toy model.
Okay. Okay.
So, if we take the final checkpoint after training here, it's not going to be the model that gives us the best performance in pre-training, in post-training, and so what we can do though is improve the coverage of the resulting base model through optimization interventions like gradient normalization, which is discussed in our paper. That's mainly for training. But what I'll talk about,
You have 5 minutes.
Okay, I mean I didn't even. Yeah. Okay. Well, maybe I'll just stop very early.
You can take a bit more than 5, but definitely.
I mean, I think I'm very not far in the talk, so yeah, I'll just stop afterwards. Yeah. So right, and then we can also use it for model selection after training using only validation data, which is related to how you can actually estimate the coverage without having access to pi star. So the model selection problem is something that actually matters a lot in pre-training the base model. And given validation data, so not pi star, but just samples from pi star, and some candidate set of base models, pi 1 through pi k, we want to output the model with the best coverage at n, which is just shown here. And we have a very simple algorithm for doing this that, at least in the test bed that I showed previously, is able to find the checkpoint with the best coverage. So in the diamond points are the models selected by our algorithm. And so these are the models with both the smallest coverage, so going left, and then the best performance going up. Whereas if you just choose the model with the minimum KL in red, what you get can be, okay, I mean the gap isn't huge here, but you can have much worse performance. And the procedure is kind of simple. So all you have to do is pre-collect log probabilities of all of your candidates on a validation data set. And the issue that I mentioned before with directly optimizing the coverage is that you need the probability of pi star. So what you can do instead is sort of treat pi star as the worst case overall models and output the model that has the best coverage over the worst case of the others. And this is just a table of numbers that you can just take the argument and argument. Okay, so as a summary, using test time scaling with best event as a problem to analyze, we came up with this mathematical model of what information in the base model, which is the coverage profile, and this gives us a sort of rule for how test time performance will scale. And this metric, which is the coverage, can also be used for improvements in pre-training to kind of optimize the properties of the base model for post-training performance. So I think I'm basically, yeah.
This is part 1. I'm just curious, can you give us an outline of the other parts and what the titles are?
Yeah.
I mean,
You can take let's say up to 5 minutes for this.
Okay, I mean, I'll give you a brief outline. I think, so the other parts are about, let's see. Let's try to do this. Okay, so the other parts were, previously I was assuming that we had a true reward model. The second half was about using a learned reward model. So here you have error, and something that's widely observed in policy optimization like DPO PPO, and also in best event shown on the right, is that I think it's more obvious on the left, but if you do post-training with R star, you see a monotonic increase in performance as training and compute is scaled. But if you have a reward model, there's this characteristic increase and then decrease, where the latter half happens because the kind of training procedure is overfitting to errors in the reward model. And this is also something that's observed in best event, where you have the kind of reward models in yellow, and there's a huge gap between the performance here and the true rewards. And also it's like non-monotonic in the sense that you increase and then dip as you overfit. And so this section is about new test time algorithms that are just like a small modification on top of best event that recover this monotonic test time scaling and get optimal statistical kind of dependencies. And I guess like the main message is just that. Let's see. I'll just give an overview here. So basically instead of best event samples and responses and queries and rewards and then outputs the best one. What we do instead is that we resample the responses according to weights in order to mitigate this overfitting to reward errors. These weights are sort of inspired by regularized RL, but what they let you do is balance like reward maximization with the uncertainty of the reward. And it's very easy to implement in the sense that you just have to compute some normalization factor, which we can do in log n time. There's maybe I'll just flash the empirical results where for GSM-8K, which is a high school math benchmark, best event performance degrades, but as n scales, then our algorithm keeps increasing. And the same is true over a number of different base models shown in different colors. I think maybe lastly I'll just say that the results that I showed previously are in this like single shot reasoning framework that treats reasoning as this contextual bandit problem and is some model for how we can leverage some properties of the base model to perform RL efficiently. And so the questions I'm interested in right now are related to sort of more realistic models for how post-training works in long horizon planning, which is the sort of paradigm that we're in right now. So the first one is models for RL beyond single shot bandit style reasoning. And I think interesting problems here are related to modeling how RL interacts with the chain of thought and how tool use helps with mitigating compounding error. A lot of our current theoretical understanding and many empirical results seem to be saying that best event is roughly speaking as good as RL, and RL is not actually moving that much beyond what's already in the base model. And I'm interested in what types of algorithms, what types of mechanisms, whether it's in like how data is designed or in the integrated algorithm itself, that we can sort of incentivize truly new capabilities. And the last one is about a lot of these problems rely on having a strong base model with natural language generalization to make RL work. But there are also many unsolved domains like chess, where we don't have natural language reasoning or chain of thought, which has driven the development of reasoning for language models. So what are some general training principles that we can take from reasoning in LLMs and take them to other domains that matter? So that's it. Thanks for listening.
We have time for a few quick questions. Yeah.
My question is about, so we have seen that LLM capabilities are limited by the pre-trained distribution. If there's no coverage in the pre-trained distribution, then there's no hope that we get coverage just by RL. So I'm wondering if anyone has tried doing something along the lines with, for example, have the large language model call external tools, then the tools automatically generate some kinds of results. For example, like in formal theorem proving, we have so-called hammer tactics, which are basically automatic search or like brute force searches that try to generate a proof for you. And then the LM could learn from the whatever search result that generates. That's going to be a proof in itself. So that could lie outside of the large language model's pre-trained distribution. And that way we could perhaps actually expand the coverage of its distribution. So I wonder if there's any research on this idea.
I think that's a great point, and I feel like many people are thinking about this right now. I mean, our understanding, like what you just mentioned, is pretty crude. Like, coverage is defined on the response space, and there are many sort of intuitive settings where you should be able to get good behavior, even though your base model doesn't, like, let's say, produce the responses you want, like the ones you mentioned. I think that it's a great question, but not a lot has been done, although I would expect people will be doing that soon.
Thank you.
Yes. I'm kind of curious about like why would this be a good model to approach this problem overall? Because like in sequence data, like the distribution that you define is like you treat every sequence like the x-axis is all the sequences, but in reality sequences depend on each other a lot. And sometimes when you flip one token, you enable a large range of your distribution to have a lot more probability. So it's kind of like more entangled than like treating all sequences like independently distributed. So there might be some modeling that goes into that, I'm not sure. So I'm basically curious, why would this be, like this kind of distribution be a good model to solve this problem, this coverage? How does it connect to like the real thing that we care about, the performance of this event? That's one thing that I'm curious about. And the other thing that I'm curious about is like one thing that hints that this might not be very connected to RL post-training is that with gradient descent, one thing that you can do is that you can flip the probability of a one token, and then that's not just amplifying, that changes the probability distribution in the whole region, because that specific token in the beginning of the sequence now has a lot more probability, and it kind of like enables you to search over a space that you never saw before, because that specific token had no probability, like weight, for example. You know, when we added weight in the sequence of like language models, we realized that they can do a lot more. They can do self-verification, which is a skill that they had. They didn't know that they had this.
I think related to the previous question, I do feel like intuitively, like policy grading should be able to do a lot more. Like best event is not the algorithm to run because it's like only searching over responses, like the whole thing. But we just don't currently really have like the results in papers that show this. And I believe it's true. I'm just saying that it's like sort of like current research. As for the first part of the question, I didn't quite understand it, but I guess I generally agree that searching over something other than responses should give you better results.
Okay, I know I also have many other questions, but I think due to time we'll end here, and you can ask more questions later when we meet with Audrey or again at 3 p.m. PhD time. Okay, thank you.